Next up, we have Brian Pailes from Vector Corrosion.
Thank you very much. My name is Brian Pailes with Vector Corrosion Services of VCS Engineering. I am the principal engineer, and my area of expertise is in the evaluation and rehabilitation of reinforced concrete infrastructure. So we're going to be talking about corrosion, but more along the lines of reinforced concrete elements here. And so today I'm going to be talking about a project here. This is the 5th Street Bridge utilizing actually a combination of galvanic and impressed current cathodic protection systems. And so this 5th Street project is actually in Courtenay, British Columbia. So in the west, but different country. So that's Vancouver Island there, you see in the image there. Victoria is kind of on the lower east there. And so you can see where that red circle, that's where Courtenay is. And so this is a steel truss structure with a reinforced concrete deck and steel girders underneath. And so the deck is exposed to seasonal chloride application, right? So that's kind of our exposure environment. And again, here's another example of what that structure is. So you can see here, this is the steel truss, which was going to get cleaned and painted, which I'm not a coatings guy. The previous guys did great jobs talking about coatings. So what we're really here to talk about today is the reinforced concrete deck, which is getting chloride exposure from de-icing chemicals over the long life of this bridge has now started to corrode and deteriorate. And then you can see the underside. Again, steel members underside, but as you can see, the longitudinal girders, the top flange is embedded into the deck. And so that is actually a concern as well, where that top flange is corroding, and so we want to provide protection to that. So what is cathodic protection? There's two forms of cathodic protection when we're talking about cathodic protection. There's galvanic and impressed current. And we kind of, when we were talking about zinc coatings just in the last few presentations, zinc is a galvanic anode. When we put zinc in electrical contact with steel, zinc will corrode, sacrificially protecting the steel. And that's galvanic corrosion. And there's actually other metals that we use in galvanic protection as well. We use magnesium or aluminum as well. However, we may use those in different applications, where aluminum you might see in, say, salt water, so bulkhead walls and submerged piles and things like that, we would maybe use aluminum. Magnesium is for pipelines and soil. We often see magnesium. But for reinforced concrete infrastructure, we're mostly going to be using zinc. And so if you directly connect the zinc to the steel, it starts giving up its electrons to protect the steel. And so that's how cathodic protection in a galvanic situation works. Well, since we're just giving up electrons from the zinc, we can get electrons from an external power source. And that's what impressed current cathodic protection is. That is where we use an external power source, usually we'll take AC power, convert it to DC, and push that onto the structure. And so now we still have an anode, but that anode is dimensionally stable, so it doesn't degrade under the current application. And now we have an external rectifier or power source that provides those electrons. So, there are ups and downs to both systems. Galvanic systems tend to be a little bit less maintenance. We can install them, they work on their own, they naturally corrode, protect the structure. But they sometimes don't have as long of a life as, say, an impressed current system. So an impressed current system, with external power source, we can provide a lot more electrons over a shorter period of time. So if we have larger structures that need a lot of protection or really harsh environments, an impressed current system may be more cost effective. Install prices are also different. Oftentimes, depending on the project, galvanic anode material costs can be higher than material costs for impressed current systems, but impressed current systems are more difficult to install. They're more technically challenging. So installation is a little bit more costly there. So at install, a lot of times they're pretty comparable install prices. It depends on the application in the system. Sometimes impressed can be actually cheaper than galvanics, and the other way around. Durability and long life. Galvanics tend to have a limit of life around 30 years. We can design them a little larger than that, but it stops being kind of cost effective. If you need a longer life, impressed current can provide a longer life, a longer protection. But now you have external electronics, and those external electronics need monitoring and maintenance. And so monitoring and maintenance with an impressed current system is really critical. And a lot of owners don't like to have monitoring and maintenance requirements after repairs. So they tend to go galvanic so they don't have to deal with that. And so, different things are, we use in different situations. And so for this project, the original engineer, he proposed to do actually a purely impressed current system where they would do a deck overlay with an impressed current mesh on the top deck to protect the top mat of reinforcing from chloride exposure. But because of the beam corrosion at localized area, what they also wanted to do was a little kind of strip and press current system on either side of the girders there. And they were kind of designing kind of this like half build out kind of thing. And you know, when we got involved, we kind of looked at that and, you know, putting kind of a build out concrete mortar on top of an existing deck, you know, that to me signals kind of an issue with debonding and, you know, trouble kind of getting that surface prep properly. And so we kind of looked at that and said, well, you know, is this really the best way to protect the top of those beams in that area? And so, you know, we started with kind of a pre-design work where we went out and really looked at the structure, kind of did a you know, corrosion potential survey, concrete sampling to understand the risk for corrosion in this deck, and then worked with the contractor and design build team to do a design system where we took the original ICCP for the top deck, but then we changed that underside to a galvanic system, which would be more effective in a targeted situation. And then my group and my team performed quality control and quality inspection for the CP system installation to make sure that, you know, went in properly per the spec and then activated the system. So, you know, first step is kind of, you know, corrosion potential survey. So understanding where the active corrosion is and the risk for corrosion in the structure. And here you see this is a survey of the top one there is the bridge deck, actually, so we surveyed the bridge deck. And then the underside is actually the survey along either side of the beam, looking at the actual corrosion activity of the top of that beam embedded in that concrete. And what we're seeing here is actually not a terrible lot of corrosion. So you see that the more hot colors, the reds and the yellows, oranges, that's where your active corrosion is going to be. And you can see on the top deck there are some areas of active corrosion, but it's not terribly bad just yet. And actually at the beam, again, we see some localized corrosion on different areas. So what we actually kind of looked at was like, you know, do we need to do full protection on the underside? Do we need to protect every square foot of that top of the beam if it's not all corroding? And with a galvanic solution on the underside, we can really do a more targeted application to protect the areas that are corroding. For the deck, though, we did decide to go more of a global with the impressed current overlay because while the activity of corrosion is moderate right now or low, the amount of chlorides in the concrete are getting up there. It is a very exposed environment. There's a lot of de-icing application. And here you can see this is an example of one chloride profile from the deck. And you can see that kind of horizontal red line was, if the chloride content is above that, that's kind of an initiation for corrosion. That's a you know, if we're above that chloride concentration, the risk for corrosion is high. And so here's one example where you can see that the chloride concentration with depth in that deck is quite high. And it varies throughout. There are some areas that are relatively low, some areas that are really high like this. But because of this kind of salt loading, even though there's not a lot of active corrosion today, we project out with service life modeling that, yes, in the next 10, 20 years, there is going to be a lot of active corrosion. So if we're going to do repairs now, doing more of a global application to the deck, which is the highly exposed environment, and doing more targeted on the underside where you're getting only moderate exposure, that is going to be a much better solution in the long term for this bridge. And so effectively, we designed an impressed current mesh overlay for the deck. So they would hydro demo the deck, put down an impressed current mesh over the deck and recast a new overlay. And so that mesh on the deck would provide cathodic protection for the entire top mat of the reinforcement. And it would throw some current down below the lower mat, but really because of the salt application on the top, we're really more concerned about the top mat. And so this is just kind of an image of showing kind of what that looks like, our connection points, the mesh over the lanes and stuff. So it's just a 2-lane structure. And then, some what the details look for like that. And so because an impressed current system requires wiring and connections to a power source, we have to run all that back to a centralized location with the monitoring station and power source. So instead of running those wires through the deck and then worrying about when we cast the overlay getting damaged, what we did in certain locations was we just punched a hole in the deck, dropped the wires down, and then ran a conduit underneath the deck. So effectively, we're able to route everything underneath the deck and hang it onto those steel girders underneath. And so this is kind of how that all connection looks like with some embedded sensors to monitor the performance. And again, just a mill, put the mesh down, and then cast an overlay. For the galvanic system on the underside, it was a drilled-in type anode. So this is what we call a type C anode, or type 2 anode, I'm sorry. And so these are drilled-in anodes. on either side of the girder to provide protection to the top of that beam and to the rebar in that zone. And these anodes are only going to be installed in areas where the risk for corrosion is high. So we're going to be cost effective with the installation on the underside because we know we don't have a global problem down here. And so the nice thing about galvanics is that we can be very targeted and cost efficient in that application. And so here you can see this is the surveys from the underside. And the little circles there are indication where, hey, this is where active corrosion is. This is where you need to put those anodes. So by doing the corrosion potential survey, we can localize where those anodes are going to go and only target what needs to be done. And so now we can have a more effective, cost-effective corrosion mitigation solution on the underside as opposed to doing kind of that full impressed current on the underside as well. So we can save a lot of money on construction and materials with this kind of application underside because the risk is lower down there. We don't have to worry as much to reach that service life. So what is that, what does the installation of all this look like? So for the deck, they're doing one lane at a time. Obviously, this is still an active bridge. So half the bridge is shut down. They mill off, the cover concrete. And then in 4-foot wide rolls, the impressed current anode mesh gets rolled out. And you can see them rolling it out right now. And then they'll pin it with some plastic pins just to hold it down in place so it doesn't bend up during casting. But this installation of the impressed current deck overlay is very cost effective and cheap because it is very easy to install. I mean, you have a big roll, you pin it down, and you start rolling it out. Take a couple of guys only a day here to get the mesh down. So relatively pretty simple to install. So for a deck, this is a pretty cheap installation application here. At some locations, they're gonna expose the steel to make bonding wires to the steel. So we need to connect to make a circuit to the reinforcing steel. One also important step, I'll just back up, wrong way, is, when we do that milling, sometimes you're gonna expose some low cover steel. So obviously we can't have that anode touching directly to that steel. So we're gonna coat that in epoxy, protect against shorts, because we want, we make those connections and then we run that all back to a power source. And then here on the right, so there on the left is the connections to the rebar. On the right there, you see that they're connecting a distribution bar to that mesh with a resistance weld. So that's how they deliver the current to the mesh and distribute the current through the anode. And so he's just connecting that together, and then they'll connect that to some wires and run that back to the rectifier. And then on placement day, so once you get the anode mesh all in place, all the connections are done, then they come in and cast the concrete and pour the overlay. And so they can walk right on it. Obviously, where the connections are, they'll want to protect those, make sure the wires are protected because it will get stepped on. They'll even drive the concrete truck over top of it. One of the big things, as long as the concrete truck, he's not turning his wheels and rubbing on the mesh too much, we've actually had the concrete truck just back right on top of it. It's titanium mesh, so it's really durable, and as it can withstand the vigors of concrete placement. So not an issue. They're placing it right on top of that. And then, the wiring. So because impressed current system has external electronics, there is, some significant wiring. And so what they'll do is they wire that system all back to some control boxes at one of the abutments on the bridge. And so this is what kind of typically that wiring and monitoring system looks like. So not only is there the wiring for the impressed current to distribute the current, but we want to monitor this. So we have Campbell Scientific data loggers in there to remotely monitor the performance of this system to ensure that this system is working properly for the owner over the life of the system. And so, it's connected in there to a modem, to some data loggers, and so we can remotely call up that system and make sure everything is working properly. So yes, the monitoring is required, but we can do it remotely very cost effectively. We don't have to send a technician there all the time. It's in the middle of nowhere in Vancouver Island, so obviously it's very costly to get to. So simple, on my phone, I can just call it up and see that the performance is good. And if there is something that ever does go wrong, then we can send a technician to address it. And so this is the wiring that's required, to kind of get that all system together. And this is what those final boxes look like. You have a wire distribution box, we have a monitoring box, and then the actual rectifier, the power source. And that, the photo on the left there, that is the actual rectifier power source. So that's taking the AC power from the city, converting it to DC current, a DC power, and putting it onto the structure. And so, again, there are external electronics in an impressed current system, so that requires monitoring and maintenance of those systems and eventual, replacement. In 15, 20 years, we'll replace all those electronics, but everything embedded in the concrete is going to last 50 plus years. So we can go to the abutment, replace these electronics when they're outdated or broken, but everything embedded in that concrete, that titanium, that's going to last a really long time. So that'll outlast the bridge. So everything we do embedded in the concrete's durable for the longevity of this structure. So the galvanic system, again, this is going to be a localized application. You can see there on the right where they have some full depth repairs. They can just put the anodes right into those repairs, connect them to the steel, and they're done. They're not wiring that to anything beyond that. So they're just connecting those in those areas where they have corrosion of the top of the steel beam, protecting that and stopping that corrosion in the area. Areas where they're not doing full repairs, they're doing a drill hole from the underside and grouting those anodes in from the underside. And again, these anodes are going in only at those targeted areas, so very localized and targeted in what they're doing. So they're not coring every single, along every single beam. They're just doing it in the areas necessary. Now, some of those zones we do monitor, just because we do have a monitoring station on that structure for the impressed current. We did wire up some zones of those anodes back to those monitoring stations so we could get some performance data off of the galvanic systems. And again, we route those wires from the location all the way back to the abutment. And so this is, again, most galvanic systems we don't monitor unless we really want to. And because we're already monitoring an impressed current system, it's a simple thing just to add a couple of monitoring zones into that. So you can see kind of how they're wiring that up. And they'll route that back in conduit back to the rectifiers and power sources there. So, Tony mentioned NACE and SSBC now being AMP. So when we look at the performance of cathodic protection systems, we really look at, NACE, those standards. NACE 216 and 290 are for impressed current. And so they have various criteria that you have to meet to make sure that you're meeting proper cathodic protection. And so there's, I won't get too much into detail about what those criteria are, but that's listed in standards that you can get from NACE, now AMP, but because those were originally NACE standards, they still have the NACE designation. And so, with the remote monitoring technologies, we can wirelessly, we have continuous data that's coming from all those zones, and you can see the one on the left is the galvanic, and the one on the right is the impressed current. And so, and then you see where we have reference electrodes embedded in concrete, and then periodically we're depolarizing the system to see that it meets the NACE criteria. And so you can see those little spikes that are happening every couple of months. Those are little depolarizations to verify the criteria is being met for NACE cathodic protection. And so this is all being automatically done by the remote monitoring system, which has a program built into it. And so we don't have to do anything. We just get a monthly report from the data logger that says, yes, everything is good. Or, hey, or zone X, Y, or Z needs to be adjusted. And so then at that point, maybe a once a year trip to the site to adjust things and make sure everything's working well is all that's needed. So the owner can be assured that he's getting what he wants and what he paid for and not having to spend a lot of money by sending technicians to a remote site. So, and with that, I'm happy to answer any questions on any of that. Thank you. Doug.
Thank you. Excellent talk, Brian. That's awesome. Good design as well. Do you do fixed voltage or fixed current typically on a project like this? And do you think at some point you'll be able to have it to be able to auto adjust based on the conditions and change in resistance of the structure?
Right. So to Doug's point, so how the current's put out from the rectifier, there's three kind of ways to do it. One is constant voltage, so the rectifier set at a voltage and has the resistivity of the concrete changes due to environmental conditions, the current flow changes. Or you could do constant current where the voltage changes to keep the current the constant, or you have those embedded reference electrodes and we can set it to say, hey, keep the potential of that reference electrode at a certain spot and adjust the voltage as you need. So in this situation, we're doing constant voltage. And typically those rectifiers are simpler, more durable, and so that's why we generally like those. With the data loggers and remote monitoring technology, you can definitely go to adjusted potential, and there are rectifiers, in the oil and gas market that use those a lot. So you have to be a little careful because if you're not paying attention to those and a reference electrode goes bad, it can send the system haywire. So we generally stay away from those unless we're really sure that we're paying close attention to them and having a lot of alarms, because reference electrodes occasionally do go bad. And in that structure, we installed extra reference electrodes that were needed from the contract because we know occasionally one will go bad, so we don't want to have to go in and replace it. But if you're adjusting your rectifier over a reference electrode and occasionally one goes bad, it could send your rectifier haywire, and that can cause problems. So generally speaking, we stay away from that just from a safety point of view, but it is a very easy thing to adjust. So.
All right, we got time for one more question over here.
I'll make it quick. What was the? I guess it's two questions. What was the decision making with the? Obviously the top of deck, you've got deterioration up there, and you've got chlorides. So that decision making seemed pretty straightforward to me. But what was the decision making for the galvanic system on the underside along the girders? What were they seeing corrosion like along the edges of the flanges? And my second question is, how did you generate those corrosion potential charts? Was that just GPS or GPR, or what was that?
Right. So your first question, they were seeing, I don't know if you guys can see it from your side, but if you see the top of the beam and the repair there, they were seeing corrosion on the top of those beams. So that was really the reason for the galvanic system to target that area. So they were getting corrosion on the top because those, I don't know, it was kind of almost a half form of crevice corrosion because the concrete wasn't quite perfectly set on top, and so they're getting oxygen and water getting in there. So that was kind of the reason for the bottom one. It was just because of those top of the beams. There was some localized corrosion. To your second point, how did we create these maps, kind of this right here? So really yes, you can use like GPS. It's really actually what we do here is we just quickly grid out the deck, and then we do a survey grid with a reference electrode device. And then we use survey contour software to actually create the heat map. So this is a grid of data that we surveyed the deck, and then we put it into a software where we can effectively create a contour, and then we color code it based on the threshold values. So this is corrosion potential half cell. Sorry, yeah, ASTM 876. So yeah.
Let's give Brian a hand.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.